today we'll be discussing about the effect of variation of field excitation on the synchronous motors. So how does it affect the motor? Now the topic of today's discussion will be effect of change of excitation on synchronous motors, V curves and inverted V curves, and effect of change in the load on the synchronous motor. So to understand what is the effect of change in the excitation, we'll keep the mechanical load as constant, and the mechanical load constant means the power drawn will be constant. So power drawn by the motor is given as Vi cos phi, and by the equation what we have derived for the synchronous motor, that is specific to the synchronous motor, is given by EV by XS into sin del, that we have neglected the armature resistance. Now in this given equation, that is the first part, P is equal to Vi cos phi, your voltage is constant, and therefore when the voltage is constant and you are keeping the power output constant, so I cos phi has to be constant. This means that if you change the current, the power factor will change. That will be in correlation, but in total your I cos phi has to be constant. Similarly, for the other equation, P is equal to EV by XS sin del, your voltage, input voltage is constant, and your reactance of the given machine will be also constant. Therefore, the variable term is your E sin del, and therefore when you change the excitation, therefore your sin del will change. So the variable quantity is your current and power factor, but the product of the two has to be constant. Similarly, your E sin del will be constant, the product of the induced EMF and the sin del will be constant, but when the induced EMF changes, the delta angle will change, that is the power angle will change. So over here if you see, this is your E, this was the initial E. So when you have changed the excitation of the machine, that is you have increased the field current, we have decreased the field current, that is the phasor diagram at constant load, and E decreases to E dash. This means the induced EMF has been decreased to E dash. This is your E, and E has reduced to E dash. When E dash is induced EMF has been reduced, the power factor angle will increase, because E dash sin del dash will be equal to E sin del, and this is your voltage. Therefore, the resultant angle ER dash also changes. Now, when your ER dash changes, naturally the current will also change, and this current will be in quadrature with the this resultant voltage, and therefore this I dash is the new current and the power factor is your phi dash. So with an decrease in the induced EMF, your power factor angle power angle increases, but your power factor angle also increases. Now if the power factor angle increases, this means that your power factor has reduced, okay, because your cos phi is equal cos phi when the angle is 0 equal to 1. So this power factor angle has increased, this means power factor has reduced. Now similarly over here you have changing the increased EMF, that is the EMF is being increased. So when you increase this excitation, in that case your voltage has changed, and the power factor over here, you can see initially the current was lagging the voltage by an angle phi, but once you have increased the excitation, the current is leading the voltage now. So this means when you change the excitation, the power factor will change from lagging to the leading part. So by changing the excitation of the current, you are reducing the power angle, and you are making the power factor angle from negative to positive, that is from lagging power factor to the leading power factor. So the effect of excitation is, that is when the synchronous motor is overexcited, it draws more current at a leading power factor from the supply mains, and a synchronous motor operating under this condition is called the synchronous condenser. Now this we have already discussed. So what is the minimum excitation? As the excitation decreases, the torque angle increases. So there has to be a limit to the decrease in excitation. So what is the maximum angle del? That is 90 degrees. So when you substitute as 90 degrees, your minimum excitation is your P excess by V. So this is your P is the power input. So with this minimum input power, the excitation is your minimum and your del will be maximum, which decides that what can be the minimum excitation for the given machine. Now these V curves and inverted V curves are very important for the given synchronous motors, because that tells you the relationship between the armature current and the field current. So over here in this figure, you can see that the curve has been drawn between the field current and the armature current, and as you change the excitation, the armature current first from the lagging power factor, it will reduce, but as you go on changing the excitation, the field current is increasing. From the lagging power factor, the machine will start operating on the leading power factor side. So this is the full load curve, this is on the half load curve, and this is your no load curve. That means the current is less at the no load and the armature current goes on increasing with the load, plus it changes with the field excitation. As we have seen before, the effect of field excitation, for the lagging power factor the current reduces, but for the leading power factor the armature current will increase. Now as the shape of these curves are in the shape of the alphabet, that is your V, hence these curves are known as V curves. Similarly, when we draw a curve or we draw the relation between the power factor and the field current, this is the curves which we get it, which is just inverse of the V, hence it is known as the inverted V graphs, and the highest point on each of these curves indicate the unity power factor. So now from at no load, from lagging power factor, when you change the field current, it goes to the leading power factor, and the power factor will be unity at the maximum over here, and later on again it reduces. So this is for the half load and this is for the full load. So this shifting of the curve from left to right happens when you increase the load, and this shape gives the inverted V curves. So the synchronous motor at full load, when it is operating at unity power factor, then the removal of the shaft load causes the motor to operate at a leading power factor. So these are the basic characteristics what we conclude after drawing these curves. So these curves are important for the analysis of the synchronous motor. Now this shows you the effect of the change in load on a synchronous motor with the help of the graphical analysis. That is, we have taken the voltage as the reference and the induced EMF is the resultant, and depending on the power factor you will get the current, whether it is leading or lagging. So over here you can find out that the machine is rotating, but the rotor slips back in space as a result of the loading. So as you increase this current, and as the power factor is changed from lagging to leading, the induced EMF also changes, and basically the del angle changes. This relationship will change because excess is constant. So if you increase the current, your drop will increase, and therefore your del angle will increase. So the increased torque increases the rotor speed, but the motor again picks up the synchronous speed with a larger power angle del. And the equation for the torque is given as T is equal to V sine del by XS is the power equation. So when you divide it by omega, you get the torque equation. So from the power equation you can obtain the torque, and this we have already concluded that with the increase in load the torque angle del increases. So you can find out the relationship as E sin del is equal to P xs by V, and P is known as the Kp, where xs by V is the constant, so it depends on a constant and the relationship with the power. So the expression shows that increase in power increases your E sin del and I cos phi. Now we'll try to analyze the effect of change in the load of the synchronous motor. So the effect of change in synchronous motor is, that is when you increase the load, the drop increases and therefore the power angle del increases. But the motor keeps on rotating at the synchronous speed. Only thing is that rotor slips back in space as a result of the increased loading. Now the torque equation can be given by T is equal to VE sin del by XS, that is your power equation. So divided by omega, you will get the torque. Now, so the increased torque increases the first the rotor speed. When you try to load the induction motor, the rotor speed will increase for momentary, but again the motor will fall back to its synchronous speed with a larger angle, power angle, that is your del. So with the increase in load, the torque angle increases, and the excitation, if you keep the excitation constant, in that case your field current and the speed, both of them will be constant, because power is equal to VE sin del by XS. So when you keep the uh, E constant, that is excitation as constant, your del will only change. Now this is the effect of load. This is the phasor diagram. You can see that the induced EMF is again changing in the circle as we have discussed in the synchronous generator case. That is, this is the limit locus of the uh, induced EMF, and as the current increases, your drop increases, and therefore your induced EMF also changes. That is, induced EMF is constant, but your angle del changes, and therefore the power also changes. That is, we say that your EF sin del is equal to V EF by XS P, and because all these are kept constant, the excitation current, the voltage, and the synchronous reactance are all constant for the given motor. So the power will be a part of the power that is being delivered. So now what do we conclude with the effect of change in synchronous motor? When the load of a synchronous motor is increased, the motor speed does not change. It will run at synchronous speed only. Only the torque angle increases. The excitation voltage remains constant if you are not increasing the field supply. So the armature current drawn from the supply increases, and the phase angle phi first increases in the leading region and then it increases in the lagging region. So it will be minimum in the case of the your it will be a unity power factor. We have seen the inverted V graph, so that will give you the relationship of the phase angle. Now there is a limit for the mechanical load to be applied to the synchronous motor. That is, we can't increase from the maximum pull-out torque, that is del should not be increased beyond the degree of a 90 degrees angle, and normally your full load torque is your pull load torque will be 1.5 to 3.5 times of the full load torque of the given synchronous motor. So today we have studied the effect of change in excitation, the V curves and the inverted V curves, which gives us the relation of the field with the armature current and the power factor, and the effect of change in load with the help of the graphical analysis we have studied for the induction synchronous motor.